Good morning everyone, this is Dr. Shivani Agarwal. Today I present the topic is RAM or ROM designing. This is the memory organization topic. So we have to start. So this is RAM or ROM designing. So what is the main memory? Basically it acts as a central storage unit in the computer system. It is a large and the fast memory. When we use to store the programs and data during the runtime operations, so we use these type of memories. So there are two types, RAM and ROM. So RAM is random access memory, ROM is read only memory. So we have to design the RAM and ROM in the circuit diagram. So RAM chips are available in the variety of size and use as per the requirement. So this is the RAM chip. So in the RAM chip the size is 128 in this particular example, but this is variable in size. So which size we want, we have to use that size particularly. So in RAM there are the four basic concepts. This is the CS1, CS2 complement, read, write and address 7. So what is CS1? CS1 is the chip select 1, CS2 is chip select 2, this is the complement of CS2, and read, write, there are the two modes, read and write modes, and the address lines. So there are the 7 address lines, because due to the size of 128, so it is basically 2 to the power 7 equal to 128. So we use the 7 as a address line. And what is 8? 8 denotes the bits. In bits, suppose this is the RAM. The size of RAM is 128 into 8. So the memory is divided into the number of words, and the address of first word is 0, and the address because the size is 128, so last word address is 127. When we want the address bits, so it is 7 bit. So the starting bits are 0, 0, 0, 4, 5, 6, 7. So these are the address bits. So these 7 bits recognized as the address bits for the first word, and this word have 8 bits. So this is the complete recognition about the 120 into 8. So there are 128 organizations, matlab 0 to 128, 127. So these 128 words save in this memory, and each word have 8 bits. So this is the complete organization of the memory RAM. So in this example we use the 120 into 8. For example, if the size of RAM is 512 into 8, so this is what? 512. 512 means we have 512 words in the memory. We have 512 words, matlab first word is 0 and the last word is 511. And what is the address bits of that? So it is 2 to the power 9, because 2 to the power 9 equal to 512. So their address bits, first bit is the 9 times 0 and the last bit is 511. So this is the 9 times 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that shows the address bits. So this is the address recognition of the RAM size. So if the RAM size is changed, then the address bits are changed, and the memory have the different words according to the size, and each word contain 8 bits or 16 bit or 32 bits. It depends on the RAM chip size. So this is the basic. Now what it means, that I already explained, that 8 bit recognize the word size, read and write. There are the two type of controls, CS1, CS2. This is used for the RAM chip select and the ROM chip select. When we use the CS1, so we have to use for the RAM chip select. We use the CS2, so it is for the RAM chip select with respect to the RAM and ROM, and the address bit depends according to the size. So this is the RAM chip. Now this is the table. Just a minute. Now this is the table. This table shows the memory functions with respect to the states. So if there are the 4 parameters, CS1 chip select 1, CS2 complement chip select 2, read and write, there are 2 type of heads. So 2 type of controls. if the chip select 1 is 0 and chip select 2 is 0, that means the memory function is the inhibited state. There is no and read and write mode is open. So the function is going to the high impedance state. What is high impedance? This is Z, represented as Z. We have already explained the Z in the bus transfer, है ना, converse system. We have to teach about the high impedance level. High impedance means the circuit behaves like an open circuit. So there is no current flow in the circuit diagram. So this is the high impedance definition. Now when the CS1 is 0, CS2 complement is 1, so it is also represented as 0. So this is the read write head, both are not enabled. So this is again goes through the inhibited state and the circuit goes through the high impedance state. When the CS1 is 1 and CS2 complement is 0, so it is both are 1 by default. So the read write head not in the working condition, it is 0, so it is again in the inhibited state and the circuit goes through the high impedance state. When the read is 1, that means we have the read state and the output data to RAM. When it is in the write state, so write is high, so we have to the write state is high function and the output comes through the input data to the RAM. When the CS1 and CS2 both are 1, that means the CS2 is 0 because it is a complementary state, and read write head again there are the don't complement state don't care state. So the circuit function goes through the inhibited state and the state comes in the high impedance state. So this is the basic table. Now we have to define for the ROM chip. So this is same as the RAM chip. The difference is that there is only a read head, not the write head, because due to the ROM this is the read only memory. By the name it also defines that. So storing an initial program, it is known as the bootstrapper, that we already know. And the size of the ROM chip in this particular example, we have to take 512 into 8. So if the size is 512, so the address bits are 9, that I already explained the RAM chip, because we have to take the size of the RAM chip is 512 into 8. So in this the address bits are 9 due to the size. If the size is changed, the address bit it change. This is the very important point that you have to find in your mind, that if the size is changed, then the address bits are changed. Because of this, if for example if we take the size is 1024 into 8, so what is the address bit size? So address bit size is 10, because 2 to power 10 equal to 1024, so the address bits are the 10. In this case the size is changed in the ROM chip. So in this chip we have to take only the size is 512 into 8, so the address bits are 9 in this case, and the chip select 1, chip select 2, and we have a read head, not the write head due to the ROM. So this is also we have to define. Now move on. So these are the chip select 1, chip select 2 corresponding to bit size and the address bit, so that I already explained. Now we have to move with the question part. So assume that a computer system needs 512 bytes. Computer system required 512 bytes of RAM and 512 bytes of ROM. The RAM chip has 128 byte. 128 byte means 128 multiplied by 8. And the ROM chip has 512 bytes, that means 512 multiplied by 8. So this is the actual size, that this is the actual chip size of RAM and ROM. But the computer system need the RAM are 512 bytes and the ROM are 512 bytes. So how we have to do this, and how many RAM and ROM chips are required for this particular designing? So this is the basic question. Now we have to move how we have to define the address in the hexadecimal formation, and how we have to define the connection diagram of that. So in this, we to make 512 into 8 RAM, and the actual RAM size is 128 into 8. So how many RAM chips are required to make the RAM is 512 into 8? So it is 512 multiply by 8, this is the size that the computer needs, and 128 into 8, this is the actual size of RAM. So by using this size, how many RAM chips are required? So these are the 128 means 2 power 9 divided by 2 power 7. This is 2 to the power 2. So there are 4 chips are required. 4 RAM chips are required for designing the RAM. And how many ROM chips are required? The size is 512 that the computer needs, and the ROM size is also 512. So it is the 1 ROM chip are required. Due to this, 512 divided by 512, so it is 1. So in this particular question, the 1 ROM chip we have to require and the 4 RAM chips we have to require. According to this question, 1 ROM chip, so 1 ROM chip and 4 RAM chips are needed. Now, this is the diagram. That table shows the hexadecimal address table of the RAM and ROM designing. So how we have to do this, how we have to define these tables. So we actually know that the hexadecimal address. So how many bits are required for the hexadecimals? It is 16. So this is basically we have to define as 1 to 16. So it is basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. These 16 bits we have to draw or define for a single hexadecimal address of our RAM or ROM. So in this we required, how many RAMs we required? 4 RAMs we have to use. So this is the RAM 1, RAM 2, RAM 3, RAM 4. 4 RAMs we have to define and a single ROM. ROM is 1. Now how we have to define the hexadecimal address for the RAM and ROM? So this is actually we have to define that the RAM chip size is 128 into 8. So we have required the 7 address bits. So these are the 7 address bits for the RAM chips. And how many address bits are required for the ROM? So these are the 9 address bits are required for the ROM. So it is the 9. Now how we have to define these crosses are there? So in the RAM chips, because the 7 bits are common for all RAMs, RAM 1, RAM 2, RAM 3, RAM 4. So in each RAM we have to use this cross for designing the address of the RAM 1, RAM 2, RAM 3, RAM 4 like that. These 4 RAM chips addresses are crossed till 7. Till 7 these all are crossed. Then how we have to move further 9 to 16, 8 to 16. So it is according to that we have 4 RAMs. So how many bits, how many binary bits are required to designate these 4 RAMs? So there are designate because of the 4 RAMs, these are taking the 2 bits. So it is 0, 0, 0, 1, 1, 0 and 1, 1. So in this the RAM 1 we have to use 0, 0. For RAM 2 we have to use 0, 1. RAM 3 we have to use 1, 0 and the RAM 4 we have to use 1, 1. These 4 bits we have to use 0, 0, 0, 1, 1, 0, 1, 1 for the RAM 1, RAM 2, RAM 3 and RAM 4. So for these definition, for these binary system we have to use 2 bits, 8th and 9th, used for the designate the type of RAM, RAM 1, RAM 2, RAM 3 or RAM 4. So these 2 bits are used for that. Now these 10th bit we have to use either RAM or ROM. So 0 we use as RAM, 1 used for ROM. So these are the bits that we have to use for designing of RAM and ROM in the address map table, memory address mapping table. Now how we take the 9 bits addresses for the RAM due to the size of RAM. So size of RAM chips are 512 into 8. So it is required for the 9 bits for the designing of ROM, and because there is only a single ROM, so we don't require any other bit for the ROM 1, ROM 2, because there is only a single ROM. But due to the RAM and ROM differentiation, so we have to designate 1 for ROM and 0 for RAM. So this is the address mapping table. Now we have to define how we have to design the connection diagram for this. So in this diagram we have to design, first we have to explain how we have to define this hexadecimal address, how we have to recognize that 00002 007F. So how we have to do this? So this is for the first RAM. First we have to define, this is the RAM 1. So if we have to define the RAM 1, so it is initially it is 00, all for the first address, all values are 0 till 16, 1 to 16, all values are 0. But when we have to define the last address of RAM 1, due to the suppose this is the RAM 1, this is 0 to 127. So the last bit are completely all ones, that I already explained, that the last chip I defined that already. Last value is 1111 till 7. Because of the address bits are 120, address bits are used as 7 because the size is 120 into 8. So the 7 bits all are 1 1 1 1 1 1. But due to the RAM 1 we have to use 8th and 9th bit are 0. So in the initial address 8 and 9 bit are 0, and in the next address, last address, we also take the same values, 8 and 9 bit are 0, and for the 10th bit we use 0 as a RAM 1. So we use 0 as the RAM 1 in there, and the other 16 bits are 0. So we have to define the hexadecimal calculation as an address from the decimal value. So they are using the 4 bits, because to get 4 equal to 16, so we take the 4 combinations on that. So this is the 4, this is F, this 4 represents 7, these 4 represent 0, and these 4 represent 0. So it is 007F. This is the last value, and the first or the initial address of RAM 1 all 0, so it is 0000. So the address of the RAM 1 is 00002 007F. So this is the defined hexadecimal address for the RAM 1. Now we have to move for the RAM 2. So in the RAM 2 the address is 0080200FF. How we have to do this? So we have to change only the 8th and 9th bit, because the 8th bit is 1. So we have to do this 1 in this case for the RAM 2, and the last it is also 01, and the 10th bit is 0. So there is no impact on the 10th bit, because all the bits are used as 0 for the RAM 1, 2, 3 and 4. But the bits are changed of 8th and 9th. So this is basically what? 4 times 1 recognized as F. So it is what? 00FF in the last address, and this is basically 1000, it is recognized as 8. So it is what? 0080200FF. So this is for the RAM 2. Okay. So according to this we have to define RAM 3. So we have to change only the bit 8 and 9. So in the 8 we use 0, and the 9th is we use 1. For the RAM 4 we use 1 1 in the place of 8 and 9th. So according to this the hexadecimal addresses are 01802 01FF, 01002 017F. I think it is clear to now. Now the CPU memory connection of the computer system demand the 4 RAM chips, size is 512 multiplied by 8. So we use the 4 RAM chips, RAM 1, RAM 2, RAM 3, RAM 4 and corresponding ROM, because there is only a single ROM. Now in this there are the read and write head. So we have to just draw lines for read and write head, and we have to just connect each and every chip of RAM, we have to connect read and write head like this. This is read, this is write, and according to the RAM 2, RAM 3, RAM 4, and 1 to 7 addresses are common to all. So we have to just connect the address 7 with the 1 to 7. This is the single line address we have to use because these are common to all the chips. But the difference between in the 8th and 9th value, so we use the decoder. The size of decoder is what? Because this is for the 4 RAM, so output are 4, so the input are 2, because the size of the decoder is n multiplied by 2 to power n. So the 2 to power n equal to 4. So what is the value of n? N is 2. So in this we use the 2:4 decoder, right? Now 0, 1, 2, 3, 4, 0 recognized for the chips gives to the chip select 1, then 1 gives to the chip select 1 for the RAM 2, 2 gives to the chip select 1 for the RAM 3, and the 3 gives to the chip select 1 to the RAM 4, because it is 0, 0, 0, 1, 1, 0 and 1, 1. So we have to give according to the input values. So the 10th bit we give 0, this is for the chip select to complement. So if we give 1, because this is the complemented, so it is actually 0, and it is same we give 1 to the RAM 2, chip select 2, so it is basically 0, same as RAM 3, RAM 4, but in the ROM we gives 1, so we give the invert value of that. So this is 1 and this is 0, and due to this 0, the chip select value is the chip select 2 value is 0 in that 1 in that, because if we give 0 with the invert input, so the output is 1. So this is same as that in the ROM chip. So these are the connections that we have to use for the RAM 1, RAM 2, RAM 3, RAM 4 and the ROM. If the ROM chips are 2, so how we have to do this? If the ROM chips are 2, so we use the size of decoder is what? 1:2 decoder we have to use. So in this we use the 1:2 decoder, and the values are we have to define by the 8th value we use for the ROM chip. So according to the question, we have to change the circuitry of the diagram and the connections according to the demand. So the second question is that if the RAM chips are 120x8 needed to provide a memory capacity of 2048. So the computer needed the 2048 bytes, but the RAM chip size is 120x8. How many address bus must be used to access 2048 bytes of memory? So we have to define the address bus that we have to define, and the common address lines for all the chips of the RAM, and size of decoder we have to define how many input and the output values of the decoder that we have to design for the RAM chip selector. So if the size of RAM is 128x8, that means the address bits are to carry 7 multiplied by 8, that means the 7 address bit we have to define, because due to the size of 120x8, so there are the 7 address bits we have to define. Now the memory demands, the computer needed the bytes are 2048x8, that means this is 2 to power 11x8. If it is 2 to power 11x8 and the RAM chips are 2 to power 7, so it is 2 to the power 11 divided by 2 to the power 7. So these are 2 to the power 4. How many RAM chips we have to define? These are the 16 RAM chips we have to use. This is the RAM 1 to RAM 15. RAM 16. These 16 RAM chips we have to required for designing this question. Now, how many address bus must be used to access the 2048 bytes of memory? When the size is 2048, so it is 2 to the power 11x8. So how many address bits are required? So there are the 11 address bits are required. Now, how many of these lines will be common to all chips? So this is depend to the size of RAM. So the RAM chip size is 120 into 8, so it took care 7. So there are the 7 address lines are required commonly to all the chips. Now, how many lines must be decoded for the chip select? So how many lines we have to design for the chip select, because due to the we have the 16 RAMs, so there are the 4 lines we have to required for decoded the chip select. And what is the size of decoder? This is the 4:16, because we have the 16 RAM chips and the decoded address lines are 4, so it is 4 multiplied by 16. So the question answer is that. These are the 16 chips, 4:16 decoder size. Now this is for this particular lecture. Thank you so much.